The next section will be on genetic algorithms and developing genetic algorithm applications. Genetic algorithms are approximate solutions to optimization-type problems. They are not exact solutions, and the problem must be geared toward trying to optimize a situation. They're conceptually based on biology and deal with many of the terms that the biologists use. The goal of genetic algorithms is to keep those guesses or possible solutions that are the best and discard those that are not, giving us a true survival of the fittest. There's many terms that we use that come from biology, including parent, which are our initial guesses, offspring, which are additional guesses that are added to the model, generation of those offspring, and our generation is added every time you add a new set of offspring. The offspring are allowed to, or the best guesses are allowed to reproduce using a splitting and crossover method. We keep the best guesses, which is elitism, so we only keep the most elite. And then we have an idea we add to the mix of mutations, which allows us to randomly adjust some of our input variables for our guesses so that we don't get stuck into causal loops. There are several assumptions that we need to make in setting up our model. We need to choose how many initial parents we're going to generate, which is how many initial guesses or options we're going to start with. We need to decide how many additional guesses or situations we're going to add, which are the offspring, how many we're going to add to it. We're going to need to know how many of the initial guesses or parents or best guesses that we're going to keep. We're going to have to decide how much mutation we're going to allow. Typically, this is very low. However, it does keep the model working. If you do not add mutation, then your model can get stuck in loops. We need to define the order and the frequency of our split points, which, as we select our best guesses, we then take and mix those guesses based on how many variables from the first one versus how many variables from the next one are we going to keep. And then we also have to decide how long we're going to let this model run. This model can run into thousands or tens of thousands or hundreds of thousands of iterations, and at some point the quality of the guesses becomes diminishing return. So you need to decide how long you're going to let it run and when you're going to stop it. There are several limitations on genetic algorithms and some limitations on our technology or our tools that we use to create these models. The genetic algorithms themselves, the problem must fit within a genetic framework. So you must have input variables that are connected to an output variable such that you can adjust those input variables and receive a change in the output variable that you're looking for. You can start getting a grouping of lesser and lesser quality answers, and so your model can start thinking that you have received the most optimal situation, although this can just be a local loop of false optimized answers, and the real optimized answer could be in another local loop, so your model could get stuck into a causal loop. Our tools, we rely on random number generation to pick our new offspring and to decide where we're going to split things. And our technology, we're using computer random number generators, and there's a couple of restrictions on theirs or problems with them. They are not consistent in how they select random numbers, and because they're based on some algorithm, they're not actually random, they just appear to be random, so you don't get actual randomness in your model. The most difficult part about genetic algorithms, actually, is the design of the model itself. So the interrelation between the input variables and the output variables. And this is really dependent on the people putting the model together and how much they know about it, how accurate they are, and how complete they are. So the next thing we're going to do is look at a spreadsheet that shows us how a genetic algorithm works. We actually have three things in here. One of the things is a random number generator. So this is to show us how inaccurate it is to get to our solution based on random number generation. We have a genetic algorithm which uses all the techniques of the genetic algorithm, and then we have Evolver, which we'll talk about in another video. Okay, so to set this up, the first thing we have is we have a group of 6 questions. These are yes or no questions. So 1 representing yes, 0 representing no. And those are the input variables. Okay, and then our output is designed to match those. Okay, so we'll start off with some random guesses, and that's what we're going to try to hit. So we're trying to get to 1, 0, 1, 1, 0, 0. Now, as a practical matter, to make this a little easier on the user, we have concatenated those into a single cell here, and we've derived those from a decimal number. So we know that if we have a 6-position binary number, in decimal, that would represent every number from 0 to 63. So to make it a little easier on the user, we have an input cell here that will generate those 1s and 0s based on the guess that you want. So we started off with 44 as our decimal representation of these 6 guesses. Okay, so then if we run the random number generator, which is over here in cells T1 through T6, we will see that the computer randomly selects 1s and 0s for those 6 positions. Now, when it does this, it is independently generating a number for each of those positions. Okay, and as I've run this several times, okay, so this took 60 times. It tried 60 different combinations before it got to the initial number that we started off with, which is 1, 0, 1, 1, 0, 0. Okay. After running this several times, that random number generator will run anywhere from a few times into a couple hundred times. It has huge variability, and when you figure that we only really have 64 possibilities, to hit it in 60 is not very good. Okay, so now that we've recognized that random number generators are inefficient, we now return to a genetic model. So a genetic model, we start off with a number of guesses, and in our case, we started off with 4 guesses. So that's row 8 through 11, and those 4 guesses were just randomly generated in all positions, and then we score those to see how close we are to getting to our number. So if we score these, we see that in row 8, we scored a 5, and in row 9, we scored a 3. So what that means is in row 8, 5 of the 6 numbers are correct. In row 9, only 3 of the numbers are correct. Okay? So then we're going to take those 4 guesses, and we're going to take the best 2. So we've moved those best 2 guesses from row 8 and 9 down to row 14 and 15. Okay? And the next thing we do is we have to split those 2 guesses based on some randomly generated location. So we've gone and generated a random split generator, which is in row N1, or in cells N1 through N5, and what the split generator is telling us is which position we're going to split those 2 best guesses and mix the information amongst them. So the first time we're going to split it on between cell 1 and 2. Then the next time we split, we're going to split between cell 5 and 6. And the next time we split, we're going to split between cell 2 and 3 and so forth. Okay, so you can see this happening in cells 14, 15, and 20 and 21. So in cell 20, cell 20A, we take the first position of our first guess, which was 14A, so that's a 1. And because we're splitting between cell 1 and 2, we then take the other cells from the second guess. So you can see all the blue matches the blue in 20. Okay? Then for our second guess in row 15, we do the same thing. We take the first position of 15A and put it in 21. And then we take all the rest of the guesses from 14 and we put those in 21 also. Okay? And after we do that, we score them. And when we score them, we come up with 4 correct guesses in 20 and 4 correct guesses in 21. Okay, in addition to that, we're going to add 2 more random guesses. So those 2 random guesses are in 22 and 23, and we score those. And we keep doing this process down through the spreadsheet. And you can see it gets quite extensive as you scan down to the spreadsheet, which you can do later. And we keep the best 2 guesses for every generation, and we keep adding guesses in every generation. And then we score them, sort them, and filter out all the undesirable guesses. Okay. Now, in addition to that, we have added mutation into our model. So if you go over to cell X28, you'll see that that row has been mutated. So what we mean by that is in cell E28, where typically or normally we would have had a yes answer or a 1, we have arbitrarily made it a 0, okay, or mutated that cell. Okay, and as we discussed in the slides, the mutation is to help keep us out of local loops. Okay, so now if we go and we look at how this ran at the top here, we can see that we had 13 failed attempts, and we did not get a genetic match. Okay, now the reason we did not get a genetic match is because in this model, we only ran through each split 1 time. Okay, if we continue to split and continue to add random guesses, eventually we will get the right answer. Now, as you scan down through the spreadsheet, you'll notice that there's tons and tons of rows and tons of guesses, but this says we only had 13 failed attempts. That's because as you cross and split, you'll start getting duplicate guesses. Okay, so what we have here is we have 13 unique guesses in amongst all these hundreds of guesses that we've taken. Okay, now I'm going to run this, and it's going to go through the whole process. And in this case, it ran, and in 6 guesses, it matched. Okay. As you run this, you can see that we got on row 36, we got a match. Okay, which was only 6 unique guesses. Okay, it doesn't always turn out that well. Sometimes it can take many more than that. And because of the brevity of our model, sometimes it doesn't achieve a match. So that covers our section on the genetic model. The evolver will be the next video. Thank you.